Hey everyone, this video walks through a simple project showcasing how LSTMs can be used to predict stock prices over time. I will first explain how to implement the model, then prepare its training and test data, train the model, and evaluate its performance. But first, what is an LSTM? LSTM stands for long short-term memory, and it's a powerful model architecture designed to predict temporal patterns. It is a type of recurrent neural network that solves the vanishing gradient problem, which is often experienced in RNNs. It does this by providing a short-term memory for RNN that can last thousands of time steps, hence long short-term memory. An LSTM unit is composed of a cell and 3 gates. These gates are the input, output, and forget gates. The cell remembers values over arbitrary time intervals, and the gates regulate the flow of information into and out of the cell. Forget gates decide what information to get rid of from the previous state, and does this by mapping the previous state and the current input to a value between 0 and 1. Onto the project, you'll need Python 3.9 or later, and the packages NumPy, Pandas, Matplotlib, then PyTorch as our main machine learning package, and then scikit-learn for data scaling. First, we need to collect our data. And to do this, we're going to go to the NASDAQ historical data page. You can see the URL. You're going to type in the ticker you want, AMD in my case, and you click on the first result. This should lead you to this page, and then you're going to select the 5-year period and download it. Then you're going to take this CSV and move it to your project directory where your code will be. And if you open it up, it should look like this. Now that we have the data, we need to pre-process it. One of the things you noticed here is all of the prices they have dollars, the dollar sign to the left of them. This doesn't allow us to just use the number in the calculations. We're going to have to remove them. And to do this, we use a pandas data frame. So we first import the pandas in line 1, and then on line 3, we create a data frame out of the CSV. Then we replace any dollar sign with an empty string, essentially removing them. And on line 5, we're converting the column from strings to floats to be able to use later. And I'm only using the closed column just to make this simple and just have one array of times. Now we have to convert the data frame column with the closing prices to a NumPy array. To do this, we first import NumPy, then we take the column and using iloc, and we convert it to a NumPy array using .values. Then we're going to need to reverse the array because if you see here, it's from newest to oldest, and we need our order to be oldest to newest. So we reverse that. And now that we have our training data, we can plot it in Matplotlib to view it. And this is what the plot should look like. Another pre-processing step we need is to scale our data. LSTMs converge quicker with scaled data. On the left side of this diagram, this represents unscaled data, and you can see the distance of the red line is much longer than the one on the right, which is scaled data, and this shows the benefit of scaling data before training. To do this, we're going to use the scikit-learn min-max scaler class. Line 1 imports the class, then line 3 we initialize the scaler, and then we fit it to our training data. Now, we should also save the scaler to be used in inference in a different file, and we do this using pickle, which is included in the Python standard library. And now that we have our data, we need to split it into our inputs and outputs. So X is our array of input arrays, and then Y is going to be the output of the corresponding outputs to each of those input arrays. On line 5, we start the sliding window where we slide through, taking windows of sequence length, and then we take after the end of the input array, take the next element, and then we put that as our expected output. Then we append both of these values to our X and Y arrays, and we return them as NumPy arrays. Now we can apply this function to our data, and I decided to use a sequence length of 30 because it's large enough to accurately make a prediction, and there's enough training data to have many training examples. Finally, we have to split our data into train and test sets, as well as convert it to tensors. I decided to use 75% of the data for training and 25% for testing. And lines 4 and 5 get the array lengths using these numbers. And lines 7 and 8 get the whole data as tensors so that we can use it for evaluation. Lines 10 and 11 get the training data, and lines 13 and 14 get the test data. Now that we have our data, it's time to work on the model definition. So we begin by setting up our parameters and layers in our init function. We set up our LSTM layer and a fully connected layer as well as other parameters. Then for the forward function, we have to call the LSTM, and then apply the fully connected layer to the output of that. So line 3 initializes the hidden state, and then line 5 initializes the solid state. These are just going to be like zeros. And line 8 calls the LSTM layer, then line 10 reshapes the tensor, and line 12 calls the fully connected layer. Now, for the model training, we first need to define our hyperparameters. After a few rounds of training, I settled on 1,000 epochs to reduce overfitting, a 0.01 learning rate, an input size of 1, since we only have one feature, and a hidden size of 50 for a decently accurate model, and one LSTM layer, meaning there aren't multiple stacked on top of each other where the output of one goes as the input to the other. Now, onto our training loop, I decided to use mean squared error loss and the atom optimizer. Line 1 initializes the model class, then line 3 initializes our loss function, line 4 initializes the optimizer, and we start the training loop on line 6. And then after that, we have to get the outputs out of all the input training data, and on line 8, we're setting all the gradient parameters to 0. Then on line 10, we calculate the loss from our expected outputs in our Y array and our actual outputs that went through the model. Lines 10, 12, and 14 apply the optimizer, and then we print our progress on 15 and 16. Finally, on line 18, we save the model to be able to use for inference later. To evaluate the performance of the model, we will run the model on the training data and then plot both the ground truth and the predictions. So line 1 switches the model mode to be used for inference. Line 2 runs the model on all the data. Lines 4 and 5 then convert the predicted and ground truth to NumPy arrays. Then we have to undo the scaling in lines 7 and 8. And then lines 10 through 14 plot the results. Now, this is what the plot will look like. It looks really good, but in reality, it's only predicting one price given 30, so it looks like it follows really well. So this isn't really a good way to visualize how our model is doing, so we need to quantify it. Now, to quantify the performance of the model, we will calculate the root mean squared error. So lines 1 and 2 gather the predictions, line 4 through 7 make them NumPy arrays, then we undo the scaling, and then we calculate and print out our RMSE scores. In my case, I get around 3 for the training score and 4 for the test score. So now that we have created, trained, and evaluated our model, it's time to use it in predictions. So we're going to start by importing our dependencies and our model definition. So line 10 imports the model definition from a file called train.py, so rename it if you have a different file name. Now we need to load our scale and model that we have saved earlier, and then we do the same thing. We switch the mode for inference again because we're working on a different file this time. Now, since our sequence length is 30 days, we need to make a function to predict the next 30 days. To do this, every time we generate a prediction, we're going to use that output as input to generate the next prediction. So in this little diagram, the gray values, those are our original inputs, and then each color has a bracket and a number. So like the red takes 1, 2, 3, 4, 5 as input and returns 6. Then we take 2, 3, 4, 5, 6 as input and return 7. And we go on for, in our case, 30 days. It doesn't make sense to go past 30 days since it won't be using any real data to make its prediction. And we take in 1, 2, 3, 4, 5, and we get out 5 days of data. Onto their code, where we first get and pre-process the data. Then we define our sequence length, which is 30 days, and then we initialize the sequence. After that, we loop through 30 times, adding all of our predictions to the predictions array to be able to be outputted later. And we just add that to be used as input to continue moving on. Now that we have then we have all 30 of our predictions, we have to undo our scaling and then save these to a CSV. So now when we apply this function, we can get 30 days of data, then we generate a prediction for the next 30 days, and we compare it to what actually happened on a plot. So lines 3 and 4 here get and pre-process the data from an input CSV, then line 6 plots that, then line 8 and 9 plot the output through the model, and lines 11 and 12 plot the ground truth. And this is what I got. This is a more accurate depiction of what the model's accuracy is like. And as you can see, so the blue line is the input, the green line is what actually happened, and the red line is the prediction. As you can see, the prediction very generally follows where the stock is going to go. So it has some accuracy, but it's not really that useful. And thanks for watching.